In this video, we are going to talk about the most important distribution in all of statistics and probably in many, many other fields called the normal distribution. So like I said, it's the most important continuous distribution that you'll ever encounter. It's used in so many different fields: biology, sociology, finance, engineering, medicine. It's just so ubiquitous throughout so many fields. So having a good understanding of it now is very transferable. Sometimes you also hear it called the Gaussian distribution. They're just two words for the same distribution. And as it turns out, that another reason why it's so important is that it turns out many real-world random variables actually follow this normal distribution. So if you look at things like the IQs of people, heights of people, measurement errors by different kinds of instruments, these can all be modeled really nicely with a normal distribution. And we know a lot about a normal distribution, both statistically and mathematically. So here's a picture of what it looks like at the bottom there. Sometimes you'll also hear it called a bell curve, because it kind of looks like the curve of a bell. And it's parameterized by two things. That's the mean, which is that lowercase mu, in other words, the average or expected value. It's really, what that denotes is where the peak is. So all normal distributions have a kind of peak. So the mean just tells you where that peak is. And then we have the standard deviation, which is the lowercase sigma. Sometimes you also see it written as sigma squared, which is called the variance. And the standard deviation tells us the spread of the data away from the mean. Basically, it just means how peaky is it. Is it kind of like flat, or is it very peaky? That's really what the standard deviation is telling you. And here is the probability density function. It looks kind of like it's kind of complicated there, but if you were to run that through some sort of graphing program, given a mean and a standard deviation, it would produce this graph. Fortunately, there are libraries that compute this for us, so we don't have to do much. We don't have to look into this too much. So another notation point I should mention is that capital letters are usually random variables, and lowercase letters are an actual specific value. So that's just a notation point. So let's talk a little bit about some of the properties of the normal distribution. So the mean, median, and mode are all equal, and they're all at the peak. They're all equal at the peak. So the peak is the mean, as we've said, and the location, the median and the mode are also the same. Another really nice property is that it's symmetric, perfectly symmetric across the mean. And that's also going to be useful for hypothesis testing, because if we know some particular value to the right of the curve, if we take the negative of that around the mean, then we'll know what the value on the other side of the curve is. And by the way, this is a true probability distribution, so the largest value is going to be less than 1. The tails are always above 0. And if you've heard this word before, asymptote, that's what they are. They're asymptotes at the x-axis. They get really infinitely close but never quite touch 0. And if you were to take the integral of this, it would actually equal 1. It's called the Gaussian integral, in case you're interested. Another neat property of the normal distribution is called the empirical rule, and this is just mostly used as a rule of thumb. And the neat thing about this is that it works for any mean and any standard deviation. It will always be true that about 68% of the data are going to be within plus minus 1 standard deviation of the mean. About 95% of the data are going to be between plus minus 2 and 99.7 between plus minus 3. And later when we get to some code, we're going to verify this so that you don't just think I'm making these numbers up. We'll verify this with a scientific library. And so again, this is just a rule that's a nice rule of thumb to know if you want to do some kind of back-of-the-hand calculation, for example. So let me put actual numbers to this, right? So suppose that I happen to know what the distribution for adult male heights are, and that is they have a mean of 70 inches and a standard deviation of 4 inches. Well, then I can be sure that if just asking one random person, there's the area under this curve, 68% of people are going to be between 66 inches and 74 inches of height. And by the time I hit 3 standard deviations, between 58 inches and 82 inches, 99.7% of people are going to be within that range there. And again, this is also going to be useful for hypothesis testing, because if we encounter someone who's, let's say, like 92 inches, it's very, very tall, we know that that's that's a data point that we didn't expect. It's in the 0.3% of data approximately. So this will be useful when we get a little all over to hypothesis testing, because that's kind of an abnormal or unusual value, and that might be an indicator as to whether this mean is correct or not, or maybe we think that, or maybe the value that we think is the mean is not actually the mean. In fact, maybe it should be a little higher, for example. So again, this will all become clear when we do hypothesis testing, but this is just a good rule to know. All right, so how do we actually compute probabilities of this with the discrete random variables? You just look at the different outcomes, and they told you what the probabilities are. This is not the case for continuous random variables. It's a bit more complicated, but again, we're going to have libraries that can compute this for us. So in addition to the probability density function, we have the cumulative density function called the CDF, and what the CDF at x represents, at some lowercase x, is equal to the probability that my random variable takes a value that is less than x. In other words, if I just pick a random sample out of my probability distribution, the cumulative density function will tell me the likelihood that I observe that value or less than that value. And doing some mathematics, it's actually equal to the area under this curve. In other words, it's equal to the integral. But again, we're not going to be doing any calculus, so don't worry. So if I want to know, again, suppose this is this example of heights. Suppose I want to know, if I were to just ask some random person, I wanted to ask them, hey, what's your height? I want to figure out what is the probability that they're going to be at least 62 inches tall. Well, how I would do that is I would use the cumulative density function, the CDF, and just plug in CDF 62, and that'll tell me what the probability is that if I ask a random person what their height is, the likelihood that they're going to be at least 62 inches tall. That's really all the cumulative density function tells us. The interesting point is that I can't ask what is the probability that I encounter someone that's exactly 62 inches. I can't ask that question because if we go by our cumulative density function, there's no area under a curve, because it's not a curve, it's just a point. It has no density to it, right? So how we compute this is we actually integrate this density function, but we can't do that because we don't have a point there. Intuitively, you can think of this as if we compute using the definition of probability, it's what are the outcomes where this is true? Well, it's 1 divided by what's all possible outcomes it can take. It can take on an infinite amount of outcomes. So hence it's equal to 0 for any particular x. One important thing to note is that the probability density function is not a probability. It's a probability density. So you have to integrate it in order to get an actual probability. Okay, it's a lot of words. So the other picture I have here on the right is to show you that complementation, or the complement, still holds for continuous density function. So suppose that I want to know, well, what's the likelihood that I encounter someone that is taller than 82 inches? Well, the CDF only tells me from negative infinity up to 82 inches. How am I going to know, how do I compute values greater than that? Well, I can take the complement, because the probability that x is greater than some value b is going to be equal to 1 minus the probability that x is less than b. And by the way, we don't have to be too worried about less than or equal to's. So I could have also said probably that x is greater than or equal to. It doesn't really matter because of this second bullet point here, that the probability of capital X equals lowercase x is equal to 0 for any x. There's no area under that curve, so we can kind of forego the less than or equal to's. So if I want to compute the probability that I encounter someone that is taller than 82 inches, that's equal to 1 minus the probability that I encounter someone that's less than 82 inches. They're just complements of each other. Okay, so that's how we can compute probabilities, and don't worry, we don't have to do this integral ourselves. There are library functions that can do this for us. So one last point that I want to impart on you is that not all variables follow the normal distribution. Many scientific papers or many things you'll read that people assume the normal distribution, but you need some kind of justification to assume that. And one thing that we'll talk about called the central limit theorem kind of gives us a justification to assume normal distributions under a very specific set of conditions. But you cannot just assume that, oh, this variable must follow the normal distribution because it's used everywhere. It's not something that we can assume. In fact, there are lots of distributions that don't follow the normal distribution. For example, here I have a picture of what's called a log normal distribution. As you can see, it's not a normal distribution because, first of all, the easy way to look at it is it's not symmetric. Normal distributions have to be symmetric. It's not. But it turns out that real-world phenomena still follow this. For example, the duration of a chess game actually follows a log normal distribution. Things like blood pressure follow the log normal distribution. Things like the comment length as in how long a comment is that people leave under some kind of online post, that also follows the log normal distribution. So a lot of random variables can follow other distributions. That's okay. We have a lot of distributions. But you can't just assume that they follow the normal distribution without doing some kind of, presenting some kind of justification. So that's just something to keep in mind. Alright, so this was just a precursor to the normal distribution. We talked a little bit about what it was and some of the nice properties of the normal distribution. We talked again about the empirical rule, as well as how we can compute probabilities from a continuous probability distribution. It's not quite as easy with a discrete one. So now that we have a little bit of information about the normal distribution, let's actually see it in practice.